Thank you for giving me the opportunity to present at the Kashiwa Dark Matter Symposium 2021. I'm going to be talking about some of my recent work on primordial black holes, especially in connection with dark matter. We are all familiar with this plot that shows which fraction of the dark matter can be in the form of primordial black holes if all of the black holes are at one particular value of the mass, shown on the x-axis in units of the solar mass. Now, this plot is wrong, even though Bernard Carr, one of the key players in this game, has since corrected it. But it begs the question, since we are never quite at one, can there be enough primordial black hole, compatibly with constraints, around to be the dark matter? And in other words, what is the maximum fraction of dark matter that can possibly be in primordial black holes? Now, that question actually depends on the choice of the mass function, the mass distribution of black holes. For instance, these three plots compare monochromatic mass functions with a log normal or power law type mass functions, and the constraints change depending on the mass function. So what is the mathematical function that maximizes the mass fraction of primordial black holes compatibly with given constraints? Well, we asked this question and we found an answer. And the answer relies in the fact that mathematically this question can be rephrased as what is the minimum norm of a vector over a convex hull, where the convex hull is defined by the given constraints. And this problem has a well-defined mathematical answer, which is given n independent constraints, the optimal function, the function that maximizes the fraction, in this case of dark matter in primordial black holes, is a linear combination of n delta functions with calculable relative weights. There's an algorithm that tells us how to calculate that. So broadly speaking, it is possible to find a viable range of masses for primordial black holes in a very, very large span of masses. And today I will talk about masses that range from the Planck scale, so roughly tens of micrograms, all the way up to stellar mass black holes. And let me start with a story that has to do with substellar mass black holes, or black holes where the mass is below the Chandrasekhar mass. These black holes are especially interesting because they give an unmistakable signature that at least some of the dark matter is in the form of black holes of non-astrophysical origin. So the question is, can we ever get a calculation that allows us to understand what is the maximal number of black hole mergers that involve one sub-Chandrasekhar mass black hole? Well, LIGO has some preliminary results out, but being a theorist, what we can do is calculate the rate of Goldilocks events, meaning events that include a sub-Chandrasekhar mass black hole as a function of the mass fraction of black holes that are light enough to be detectable, that are massive enough to be detectable, or light enough to be sub-Chandrasekhar. And we carried out this exercise, which is sort of analog to the exercise of what is the maximal mass fraction of black holes as dark matter. And so, for instance, given all constraints that are known and viable at the moment, one can calculate both the maximum merger rate mass function and the minimum merger rate mass function that contains a given fraction of light and yet detectable black holes for LIGO. And one can actually plot curves of minimum and maximum merger rates in the plane of the fraction of black holes in the Goldilocks region versus the fraction of black holes that constitute the dark matter. And in much of this parameter space, the event rate at LIGO is in fact detectable. The absolute maximum is more than 10 events per year at advanced LIGO. Now, let me tell you a little bit about asteroid mass black holes. Here, one of the main findings in my group is that microlensing is actually a lot trickier than we previously thought. And in fact, it affects a large fraction of this parameter space, and it has to do with the fact that constraints based on microlensing underestimated the effect of stars being large compared to the point source sensitivity of the hypersupreme Subaru camera that was used in observations of the Andromeda Galaxy to constrain primordial black holes. In fact, the bigger the star, the more important final source size effects are. And as it turns out, taking into account the real mass distribution of stars used in HSC constraints on microlensing, we realized that the actual constraints are a lot weaker than what initially thought. And there is a very large swath of parameter space that is completely viable where primordial black holes can in principle be 100% of the dark matter. So the question is, of course, how do we go after them? And we've done some work in trying to understand the capture and perturbation rate of disaster mass black holes around pulsars. Femtolensing also has similar finite size source effects that eliminate constraints in the lighter black hole mass region, a region that I'd like to draw your attention to next. These are sort of 10 to the 16 or pyramid mass black holes that are currently in the process of evaporating. So black holes, in order to be the dark matter, must be long-lived enough. And in order for that to happen, they have to have a mass on the order or heavier than 10 to the 15 grams. This is the relation between the mass and the lifetime of the black hole to Hawking evaporation. And that in turn sets the scale of the Hawking temperature of the evaporating black holes to be around an MeV. So the best telescopes in the MeV range that are available right now are listed here. And with two of my former graduate students, Logan Morrison and Adam Coogan, we've calculated in detail the spectrum from the evaporation of black holes that possess a Hawking temperature around the MeV. And notice that this is significantly different from predictions that were obtained by the code Black Hawk, as well as by previous simple estimates based on the geometric optics approximation. Now, Black Hole does incorporate our results that were published in Physical Review Letters earlier this year. And the constraints we obtained show that COMTEL is, at the moment, the most competitive telescope in this mass range. And the future telescopes, especially GECKO, will outperform by several orders of magnitude the current constraints in this mass range. And I point you to a couple of papers to study the potential of future MeV telescopes in the MeV, including in connection with evaporating black holes. Now, lighter black holes are too light to be stable today, but they can still be relevant for the dark matter in that they do evaporate and they could produce, in principle, dark matter in the process of evaporation. So we studied this in 2019, and we showed that in the parameter space described by the relative initial abundance of PBH to everything else versus the PBH mass, regions are excluded by a variety of constraints. But given a dark matter mass, it is possible to both produce the dark matter in the right abundance and perform leptogenesis in producing, through evaporation, right-handed neutrinos in the right amount. Now, more recently, we have also pointed out that the evaporation of black holes can also induce directly baryogenesis by a coupling of the Kretschmann scalar to a B-L current. And so if evaporation then stops at some point, indicated here on the vertical axis, it is possible to produce the right amount of baryon symmetry from the time variation of the Kretschmann scalar as coupled to the B-L current, as well as the dark matter, as long as the radic have mass in this vertical axis scale. Here, the M star on the horizontal axis indicates the suppression scale of this additional operator that we postulate exists and triggers the production on the event horizon of the black hole of a biased baryon number density. As the black holes approach the Planck scale, they generically acquire a radic electric charge, something that was recognized long ago. This can also stop evaporation because of extremality due to the fact that the metric of the black hole changes when the black hole gets charged. And so this leads me to the last topic I want to discuss with you today, which is grain of salt black holes that weigh about 10 to the negative 3 grams. We studied this in a paper in 2019, and we showed that by far the best constraints come or will come from paleo detectors. Even a centimeter squared Pali detector with sufficient purity is able to test relics on the Planck scale, even if the relics are only a few parts in 1,000 of the dark matter for that particular mass. Now, there have been claims that Hawking radiation would impart sufficient kicks to the relics at the Planck scale to make the dark matter too hot. Well, this is only true if evaporation stops very late in the game. In fact, it has to stop much later than BBN, which cannot happen because of BBN constraints. And so we've got a brief note out from May this year with my student Ben Lemon, where we show that black hole remnants are in fact never too fast to be the dark matter, so they're perfectly fine as dark matter candidates. So today, I told you a little bit about stellar mass black holes. Sub-transsacral mass are a Goldilocks signature for PBH's dark matter. How do they arise? Well, that's not clear. That's in fact something we are currently working on, and we think that the best way to generate sub-transsacral mass black holes from a dark sector is with a dark sector that encompasses some dark QED without dark nuclear interactions. It is not easy to do things properly. Previous groups have tried to do this calculation, but we think that some important effects have been neglected. Secondly, I've told you about asteroid mass black holes with a mass around 10 to the 22 grams. Here, microlensing is a lot trickier than previously thought, but it also offers opportunities, especially when it comes to future large-scale surveys. Evanescent black holes, or black holes with a mass of around the pyramid, are constrained best at the moment by CONTEL, but I've emphasized how future MEV telescopes will indeed promise much better constraints, and how tricky the calculation is of the gamma ray spectrum that cannot be performed using tools like Pythia, but has to rely on a proper treatment of hadronization of low energy quarks emitted by Hawking evaporation. Finally, ton-sized black holes whose decay produce dark matter can also produce dark matter through Kretschmann scalar coupling to beam inside currents, and can produce dark matter also as a result of Planck relics of evaporation. In turn, these Planck relics might be detectable as long as they carry an electric charge. So they are detectable, presumably with Pali detectors, and generally they're not too fast. To close, I'd like to state that in the era of gravitational wave astronomy, the physics of macroscopic dark matter candidates offers many opportunities for the ingenuity of theorists and the craft of observers alike. And I look forward to having a discussion with all of you on Slack. Apologies for not making it live. It's 3 a.m. my time zone, but thank you for your attention.